Oh, wow. Okay, I think it's working. Great. So I think what to do is try to try to talk about Nakamoto for a little bit. I just touched my face on the screen. I just saw that. Um, okay, so let's see. So I'm going to try to talk about Nakamoto consensus here. Let's see. So the way to do this, I think, would be to create a new PDF, um, and I should be able to share this at the end. And then let me check. I need to make the display capture available, and let's see, this view mode should be in single, and hopefully that looks good. I guess maybe let's see if I can do this any differently. Since I'm just practicing. Okay, so let me try to talk about Nakamoto consensus. I'm reading the paper by Ling Ren. It's only 6 pages long. So yeah, let's see. Okay, so so let's see. So this paper is called is called sure, crypto. Okay. This paper is called Analysis of Nakamoto Consensus. Um, and most people know about Nakamoto because of Bitcoin. And it's a form of Byzantine fault tolerance consensus. And it centers around proof of work. And it has this rule called the longest chain is wins. Great. So, what, every time, basically, that an honest node adopts the longest chain and attempts to mine a new block, it's basically trying to extend this longest chain, and this block is committed when it's deep enough in the chain, whatever that means. Okay. So the model involves these blocks, like I said, and each block is linked to the previous block via this concept of proof of work. And this is what forms a proof of work chain. Now, the height of this block, the height of a block has to do with how long the chain is. So if I keep going, let's see, so maybe you would say the length of this chain is 5, and the height of this block is 5. And honest users can gain new blocks either by mining them themselves or by receiving blocks from other users. There's 2 things that the consensus has to give you, which is, first of all, safety, and the second thing is liveness. We've talked about safety and liveness before in the reading group. So take a moment to think what is safety and what is liveness. Okay, so safety means honest nodes do not commit different blocks. At the same height. And liveness means every transaction is eventually committed by honest nodes. Okay. So the liveness property sometimes gets split up into two different things, one of which is called chain growth, and the other one is called chain quality. And basically that means when you combine these two together, you say that honest blocks get added to the longest chain. In this paper, they're going to make some additional assumptions. One is called mining as memoryless, and two, the global mining rate does not change, and three, communication is delayed by an upper bound of big delta. Now we have to introduce a little bit of notation, and that notation is alpha and beta. Alpha is the mining rate of honest blocks, and beta is the same thing, but for malicious nodes. I should say honest nodes and malicious nodes. Using the fact that mining is memoryless and that global mining rate does not change, you can guess maybe what kind of process is this mining what kind of process tells you what the blocks that are mined are. The number of honest or malicious blocks mined is what kind of process. Okay, so memoryless should give you a hint, which is that it's a Poisson process. Poisson. Great. So next, if a group of nodes have have zero communication delay between them, then they can extend basically just at the mining rate. And we should say that this is true if we have malicious nodes. However, honest nodes are going to be delayed with a communication factor of at most delta. Oh, I made a mistake. So this should not be alpha. This is for malicious nodes, and they can actually do this at beta. But for honest nodes, they have that communication delta delay, and that means that there's going to be some sort of there's going to be some sort of bounded loss to mining rate. So then we need to be able to make some sort of claim about what kind of loss you can have in the honest mining rate, and so then you have to talk about the effective honest mining rate, which should be at least g of alpha, g times alpha for liveness, and g squared alpha for safety, where g is this value e to the negative alpha delta, and that should be less than 1. So the conclusion that you make here is Nakamoto's protocol solves consensus. Nakamoto's protocol solves consensus if the effective honest mining rate is larger than the malicious mining rate, i.e., you need to have g squared alpha be greater than 1 plus little delta times beta for some constant delta greater than 0. One more note to have is that delta is much smaller than 1 over alpha, and sorry, if big delta is much smaller than the than 1 over alpha, then the communication delay is very small compared to the expected block interval. And in this case, remember, so we have g is equal to the e to the negative alpha delta, but if e is very small, if delta is really small, then this value is nearly 0, and this is going to go to about 1 in that case, and so will g squared. And this is equivalent to the honest majority assumption. Cool. So next, so I think we've introduced all the notation we need, which is alpha, beta, g, big delta, yeah, and I guess I also talked about little delta. So now we're ready to do, to talk about some proofs. Let's see. We need to review what a Poisson process looks like. And we can make some conclusions when talking about a Poisson process. If the Poisson process has a rate of lambda, then the amount of blocks mined in a time interval t1 to t2 is going to be independent of all over other intervals. So something like this. How many events occur here is totally independent of what events occurred here. That's what it means to be a Poisson process. And and the distribution is going to look like lambda t2 minus t1. Now the way that a Poisson process looks is going to end up having a cumulative distribution function, p, the probability of t greater than t, is equal to e to the negative lambda t. So we saw this already because that's what g G looks like. Right here. So suppose that SK, well, we need some more notation, which is SK is the arrival time of the kth event. Then SK is the sum of KIID exponential distributions. Where IID stands for independent, and identically distributed. Okay. And this happens to be an Erlang distribution, which I am less familiar with than the Poisson process. So one thing we should maybe take a note of here is that let's make sure we understand what is the definition of a Poisson process, what is the definition of a cumulative distribution function, and what is the definition of an Erlang distribution. Great. So the next thing we want to do then is maybe try to go to the next page. Apparently. Don't even want articles fully. Okay. And now we can talk about some lemmas. These are pretty standard in literature, which have to do with the Chernoff bound. So lemma 1 is Chernoff. And Chernoff is x is equal I equals 1 to the n xi. And xi is a Boolean random variable. And these are all independent of one another. Mu is going to be the expectation of x. Then, if for delta between 0 and 1, the probability that x is greater than 1 plus delta greater than 1 plus delta times mu is less than e to the negative omega of delta, little delta squared mu. And the probability that x is less than 1 minus delta mu is less than e to the negative omega delta squared mu as well. So this means that somehow most of where x lives is between 1 minus delta mu and 1 plus delta mu. And this is what's called the Chernoff bound. And you might be a little bit confused because you're wondering, why am I suddenly talking about Chernoff? The Chernoff bound is pretty much identical to the Poisson tail bound. So we're not going to go over the proof of this right now, maybe a little bit later. So wait. The next lemma we want has to do with the Poisson tail. And what does this say? This says if x is a Poisson random variable with rate mu, then mu is also the expectation, by the way, of x. Then, with little delta between 0 and 1, the probability that x is greater than 1 plus delta mu is less than e to the negative delta squared mu. And you could probably guess the next part. It looks exactly like the Chernoff bound. And again, we're just going to wait on the proof here. We'll wait. Finally, we are going to have a lemma for the air-long tail. And remember when we talked about the air-long tail, we talked about SK. What was SK? Right, so it was the arrival time of the kth event in a Poisson process with rate lambda. Then you can say, again, for delta, little delta between 0 and 1, the probability that SK is less than K over 1 plus delta lambda is less than e to the negative mu delta squared k. And similarly, the probability that sk is greater than k 1 minus delta lambda is less than e to the negative omega delta squared k. Okay. And again, proof. Alright, so I'm going to break this up. I am going to